you should consider seriously, sort of. So Michal has advertised exponential random graph models. Generally, I agree with that, but you need to consider the features of these models as well. Depending on what you want to do, they may not always be the best choice, or you might have to think a bit more about which specifications you actually want to use, rather than take accepted defaults. So I want to say a little bit about mechanisms and so on. So there's a lot of overlap with what has been said already. There is no Coleman boat. This is why I started the video. There is only one cascade mechanism that I actually want to address, and it's not the types of cascades that we have heard about today, which were opinion cascades unfolding on a network, or at least we had heard about them, but cascades of that happen inside the networks, network formation cascade. And then contrast this with the aims of empirical data analysis, then say what people dealing with cascades have come up with for empirical analysis. And the last point, actually, it's not about emergence, it's just a summary one, sort of. Okay, background. Why do we do social network analysis? We have heard this a couple of times. Now we have theories that we may want to test at the micro level. We may be interested on top of that, or only in studying outcomes on the macro level, and we need micro level models for that. And if we have data, we can test these theories. Otherwise, we just inject them and then simulate. The idea of simulation, Epstein has been mentioned, the principle of generative sufficiency. If you want to actually explain something, you should at least be able to grow it according to an agent-based model or to another model. To that, one can add, say, the portfolio of exploring counterfactual scenarios, modifying parameters, modifying input data, or applying some distortions, and that could lead us to maybe some sort of causal understanding of how social networks actually work. Yes. And the empirical researcher wants to couple that with
Science of life.
And this is sort of what does this have to do here? It looks almost like networks, right? So, I think in terms of our understanding of society, we are not so very far yet. The mechanisms we typically talk about, they're very small. You will see some examples. We are not even at the prebiotic synthesis, I guess. Although, of course, people do organization research, and organization as such provides a sort of framework for how social relations should be structured in departments. And so that there are these designed elements of networks as well, which of course also belong here. Okay, the idea is to move from simple building blocks to more complex ones. And this is also the idea of this whole mechanistic approach. So social network mechanisms are stepping stone, sort of, in between theory and analysis. Theory gives us our stories that we tell about how we think the world works. And then a mechanism, at least in my way of presenting it here, is a rather a-theoretical thing where you have an input and an output configuration, and in between the mechanism happens. That's mechanism. So I wouldn't call, for example, a variable a mechanism. This is, but they need to be concrete. I will give a list. And of course, you know these lists from paper by Christoph and Viviana, for example, in the analytical sociology book. This is sort of an adaptation of that, what you will see here. They have proven to be very useful for empirical analysis. And in particular, when you obey some principles, if you are interested in modeling some slightly more complex things, for example, that then you should include the simpler sub-things of which it is composed into your model specification. This is, in principle, the hierarchy. It is the hierarchy principle in statistical modeling, just applied to network structures. And it is even on a very mathematical basis, sort of an equivalent thing, because these higher order structures in networks, they appear as higher order interactions of binary terms in the statistics. And if you then apply the hierarchy principle from statistics, that you should, before estimating higher order interactions, always include the lower order interaction terms, then that leads you automatically to all the subgraphs that this more complex graph has, that you also should include. And so there are actually quite close parallel considerations in useful modeling from general statistics and for network statistics. Here we have them. So this is the typical thing. Christoph draws them with that configuration with one tile dashed. And here I just have the input and the output. What you see here is from the viewpoint of the changing tile, xij, what the configuration is actually conditions the emergence of that tile. Okay. This is German. Oh, yeah.
That's why. I didn't know that. You mechanism.
There are two that I actually would call mechanisms that generate cascades. And a cascade mechanism is one where the output is actually more of its own input. I think this is a quite easy definition, even for contagion cascades now. So that you have more people being exposed by the contagion having proceeded a little bit. These two are, for example, famous MIUR effect. When somebody chooses somebody already as an advisor, for example, then I may choose that advisor too. This is, say, boiled down to just to try it. And of course, there may be more specific formulations of the MIUR effect, that this is proportional to the in degree or so, like in Barabasi's model. But the basic structure is this. And of course, this here is twice the incoming tile. So in the next round, that may lead to more. The other thing that I want to talk about now is actually the transitivity, the clustering thing. And there it's not entirely clear why the emergence of this tile would actually constitute more incentives for tiles to close. But I think when I show you the example of clustering cascades, this is going to become clear. Yeah, well, this is just a practice. I tend to evaluate whenever I get empirical data, I tend to evaluate it in terms of probability indices that are defined as the fraction of those configurations among those two. And so the degree to which the mechanism goes to the right here, or to the left, if it's below the density. Density is then always the benchmark. This is the unconditional probability of forming the tie. And all these indices, they give the conditional probability of forming that tie under the, say, the conditioning structure that we have seen. And in principle, because I teach that as a statistics course, as soon as density differs from those indices, that is evidence for interdependence of the data sets. So just based on basic probability theory, when the unconditional differs from the conditional, then there is dependence. And here we can very easily see this. Okay, we also see that, for example, the popularity network has quite a different configuration of indices compared to others. Yeah, you can use this as, say, first order assessments of mechanisms. to what degree there may be evidence for the operation of such mechanisms in your data set. I think they are not all of them are used as conditional probability indices. There are a lot of alternatives for how reciprocation or transitivity or homophily group assortativity so are actually defined, and I would actually propose to use those here more often. Okay, I skipped this slide. Idea here is just that you should actually identify the substructures, and that gives you a whole bunch, and that means you have already for relatively small things quite a big model specification, which means you probably cannot estimate the whole model specification on a small school class data set anymore, and you need larger data sets. Okay, but I wanted to talk about cascades. I mentioned the cascades in of Balabasi type. What maybe also this is the status cascades that you can get. What I think is good to remember is that Balabasi is maybe not the first to actually have thought about them. In a way, of course, he was the first to really generate the model, to come up with a model where preferential attachment in a growing network leads to the scale-free distribution, the power law distributions. However, the same phenomenon, of course, has been known for much longer. The old name is the sociodynamic effect from Moreno and Jennings from 1938. This is 60 years before Balabasi, actually. So there has been quite a history of that kind of. Instead of going into that, I'd like to illustrate the clustering cascades because they are really, they come from empirical analysis and they work as follows. Suppose you have a network like this, it's about transitive closure, and now in an undirected network, some component, some connected network or so, and somewhere a first clustering happens. So we have here the input configuration, which then gets transformed into the output. Now that we have the output plus additional connections to the outside world, this is the additional ingredient that we need here. We can recolor this in terms of incentives for the next mechanistic step to happen. And we see there are more of them. So it's likely that this person actually will be pulled into that group over time. So we have here this person connecting first here and then there. If it happens like that, of course, here also things may happen. And in empirical models, we typically mix all the opportunities. But this diagram here illustrates a little bit of how such a cascade works. So it's growing essentially, etc. The end result of such a clustering cascade is a fully connected graph. At least if you are not able in your model to halt the process at some point. And this proved to be difficult. This is the root of degeneracy problems, or at least the historical first case where degeneracy problems were signaled. Here's a sort of mathematical abbreviation of size k, completely connected, which has one more person attached peripherally to it, provides to one person. So then there are k minus one others to which this person is not yet attracted. Well, one triangle could be closed by attaching to one of the people in the clique, except for the first one that already is connected. Then next situation, there are k minus two others left, which are not yet connected. But if you close them, the tie to one of them, then you simultaneously close two triangles because you already have two people in that group. And so this actually is a higher incentive that this will happen. And so on, it goes on until the person can, with one tie, close k minus one triangles, actually, by connecting to the last one. If we sum that up, we get this kind of sum. And if we count out what that means, then we find out that it's cubic in k. whereas the time number increases only linearly in k. And that means that actually we have a thing that we cannot linearly counterbalance with a simple cost effect, cost of time creation. This caused problems in the estimation of exponential random graph models with a linear triangle count term. Okay. Empirically, these clustering cascades actually were they came up in exponential random graph modeling in the context of people not being able to deal with transitive closure estimated in a linear way. People were wondering why they couldn't get maximum likelihood estimates, while they could get maximum pseudo likelihood estimates, which delivered in simulations very strange networks, which were completely clustered, as I will show you in an example, almost completely clustered. And in these simulation studies, Hancock and Snyders, they were investigating how that exactly happens. So these processes that I was just showing you, this is basically what they found. And yeah, this is something that an empirical model should not have. It leads actually to a modeling of observed transitivity by two unobserved extremes. And so average number of transitive triplets that you have in your data set, the observed number is modeled as an average of almost empty networks and some completely full networks, which is a bad model. If you wouldn't model reality as a mixture of two unrealistic states. Okay, I skipped the hub formation stuff. In real networks, we have this moderate evidence, and the linear modeling just is bad. Just including a linear trend to close transitive triplets is a bad way of modeling from an empirical point of view. And what people came up with is then the so-called geometrically weighted specifications that we know now. But what they do is they stop these cascades. They just stop them by default. You can't get them anymore. And the reason is that instead of having this increase here, they put a cap on by weighting the number of ties with the geometric weight. Now, of course, all the polynomial things that we saw, cubic, they actually are dominated by the geometric weights. And that means there is a maximum, a theoretical maximum to what this statistic can obtain in your objective function or in your potential function in the case of the exponential random graph model. But that means indeed that the number of networks, the number of triangles actually is limited. So you cannot get things that, if you are interested in cascades, you might actually want to generate. And this is actually my sort of my contribution here. I would like to know from agent-based models perspective what they think about these kinds of interventions that empirical researchers have done with their models to make them useful for their purposes. Does it mean that they have been made unuseful for people who may not put such a corset on the networks that are generated? Here we see how such networks look like. This is just estimated on a simple example: 50 girls drinking alcohol in Scotland. Our standard. If I would tell you, this is a sort of student test. So if I would tell you which of these three is the odd one out, I hope most of you would say the one on the right. The reason being that we get here these complete clusters. Now they have transitivity close to 1. these subgroups, while, well, this is sort of a better model of this data set than the ABMs. Yeah. So much. So I'm wondering what age-based models can learn from empirical, from exponential random graph models. The idea that you should probably use them is a good one, I think. But you should be aware of these things, you know, that people coming up with exponential random graph models have solved in the past for, well, the way they thought they should solve it. It helps for empirical analysis, but it may not do what you actually want to do. And if you use these models with geometrically weighted specifications, be aware that you will not be able to get clustering cascades. What you put in, you get out, sort of. Of course, it's a bit more complicated than that because we have this feedback process inherent in this. So I think this is here the warning of Coleman from the 1990 Foundations book. I think we don't do that. We don't do quite that when we impose these geometrically weighted specifications, but it gets into that direction again. Thank you.
Thank you, Christian. Brilliant talk. We have 5 minutes for questions. Question?
I seem to have the role of asking the first question. So,
I look at you.
why not? Thank you, Christian. Very insightful. I mean, I cannot speak for the whole ABM community, of course, but my thought would be, this is an ad hoc solution if we think about it from the social mechanism point of view. And one would wonder, under which conditions does it make sense to assume that this is the outcome of the process, and where does it not make sense? So you would want to drill deeper and think about the underlying dynamic or the underlying process. One thought I could have as well, there's this old Coombs saying about good things satiate, bad things escalate. So creating more ties probably at some point would result in increasing marginal costs and probably decreasing marginal benefits. Yeah. And if one would explicate that, wouldn't you end up in the end with the same result, but perhaps with parameters you can fit better to the data?
Any nonlinear transformation might help. It doesn't need to be geometric weighting. It could curve it by taking the square root, maybe, or any logarithm. Yeah. Correct. And indeed, here it makes sense to say, well, that additional person doesn't make such a difference. If it's 10 or 11, yeah, who cares if it's not a football team?
Yeah, just standard utility maximization assumptions.
Yeah, and for status, why would that be different? Why should I attribute status to somebody who already receives so much status?
Questions? Think about it. Yeah.
So, first of all, I mean, so you can have 2 of these effects in one model, right? Yeah, I mean, yes. For example, you can have 2. Yes, so you can have the in degree, the 2 in star, for example, and the geometrically, or you can have all sort of combinations with different decay values. So it doesn't have to be that it's like this exactly. It could go differently. It's just that given that you use one effect, just as in a linear regression, you either have a linear effect or maybe you have a curvilinear effect, but you don't have anything more complex than that. You can't have like a line that doesn't go this way. And so that doesn't go like with one curve. So you could, in principle, add more complexity to it. The question is, what does this complexity add? And theoretically, does it make sense to do it? When I think, for example, exactly what you were saying, if I think about the closed triads, it's because having 1 common friend is very different from 0 common friends, but having 11 common friends versus 10 is not that different. When you think about the MIUR effect, it's more about, okay, maybe there's some people that are more attractive than others and more people want to be connected with them, but there is a limit to that, to how much a person can deal with. Now you could say, okay, we can do this with a curvilinear effect, or you could say, okay, we could have 2 opposing forces, one that drives the variation and another one that limits that variation, the cost part to it and the propensity part to it, for example. That would be a different way of doing the same thing. You basically have 2 effects, the decay value and the effect for the parameter, but you basically reparameterize, something like that, basically the effect. That's the question, whether we should do it different.
Any other? If not, I have myself. I may. Yeah, this is an interesting point in the sense that, again, I don't want to speak to the ABM community as the other gentleman was claiming before, but I see a lot of value in reversing this thing in the sense that if I'm interested to understand the emergence of social networks patterns, for instance, right? If I prove that the same kind of patterns can be generated by different type of macro assumptions, is a proof. So, for instance, if I can, with the model, explore different macro assumptions that generate equal type of structure, this, in my understanding, is a proof of the fact that it's likely that this kind of structure will happen in social network, because I can rule out the fact that it can be generated by different type of macro assumption. People can vary it a little bit in their macro behaviors, but they generate the same type of social type of structure, which is impossible here, because here the arrow is reversed, which is possible, in my opinion, with the ABM, which I can explore this kind of macro. I don't fit macro with the macro, but I generate the same macro with different type of macro assumption. In my opinion, is a stronger proof of the fact that that kind of microstructure is likely to emerge in different kind of contexts according to a variation of different type of possible belief, which accommodate the fact that individual behavior could vary, by definition, right now.
I think that can be a component or a parallelized that as well in exponential and graph models. This principle, hierarchy principle that I mentioned, it doesn't mean you need to include all these substructures for being able to generate the data that look like empirical data. Just one set of set of mechanisms that connect the empty network to the observed network. So you have a complicated structure. One substructure of that would suffice, and one substructure of that one would also suffice for being able to generate a data set that has this amount of these substructures. And
but those kind of structure must be generated according to the capacity of humans to do it.
True. Yes.
So in a sense that.
Yeah, but you can also.
But it's possible.
Different specifications.
That's true.
Interesting, nice talk. Thank you. I'm thinking another way of thinking about this cascade problem is, of course, where you end up. That you end up in a situation where it's unlikely to change. So basically, some stochastic equilibrium, which is like a sink, so you never get out of it. And of course, you say, what can ABM learn from ERGM? And I can't speak for the ABM community, but I think often when we define models, or when models are defined, we end up in these sinks, like extreme polarization, where there's no way to get out again, complete consensus, but there's no way to get out again. And I think these are certainly parallels to this example in the sense of the stochastic.
Sure, but we can't fit others that. Because they already are in states.
Yes, exactly. So was in a sense thinking about the question in the header.
Okay, so it seems that you did a good job in stimulating all this discussion. So thank you very much, Christian, for your talk. And this next one, slides.
So I guess school's out for the children. outside, but not for us. We have 2 more to go. This gives me the time to thank the organizers, and it has been a nice day, intensive, I must say. So, yeah. Oh, you do.
Can you talk about the Tolsma vote in the meantime? It would be nice. What is your opinion?
My opinion is, well, I recently had my inaugural lecture, and I had a Coleman vote in it, and I wanted to be creative, so I put I had a picture of a bathtub with Coleman in it. But in my audience, there was Professor Werner Raub, and he was a little bit offended that. Then my colleagues, some of them were also offended by saying, "Okay, you're giving a serious lecture, your inaugural lecture, and then you're showing a picture of your bathroom, right? That's your private information." But it was not a picture of my private bathroom; it was just a picture I got from the internet.
Yeah, Coleman's bathroom.
Yeah, from Coleman's bathroom. So, anyways, I never dare to show you Coleman's bathroom anymore.
It's the wrong audience.
Yes, it was the wrong audience. I should have done it here. Well, anyways, I hope I can grab your attention for 20 minutes without a bathtub. I'm going to give a talk about Arshena two-step, and I had a coffee, so hopefully it's a bit more cheery as Miranda had. Yeah, I more or less assumed that you were a little bit familiar with Arshena, but I also noticed during coffee that not everyone is. So my apologies beforehand. Okay. So it's team science, of course. So I work together with colleagues from Groningen, Marijtje, Christian, student assistant Niels, but also with Andreas and Tom Snijders. It's also open science, so please check out the GitHub website and package. Yeah, so let's get going. So this is me. So my research focuses on social divisions between groups, and which is, I think, where the interplay of inequality, polarization, and segregation. Inequality is the unequal distribution of resources, polarization is the unequal distribution of opinions and behavior, and segregation is the unequal distribution of positions. And I'm interested in explaining that by microprocesses. So imagine here what's bad for if you want, and its influence adoption processes and selection. So this is where I come from. And I want to explain polarization and segregation. And I was thinking about how does that work? Yeah, so that's my political motivation. I also have a methodological motivation, which is Arshena. I've been teaching social network analysis for quite some time now at different universities. And when I explain this to my students, I say, okay, let's suppose we have 2 networks observed at 2 different time points. How do we get from this network to the other network? And then they never come up with the mini step. And they think, okay, well, we can just jump from this network to that network. Right? But in Arshena, we actually make an assumption that we have mini step, that only one actor is allowed to change one outgoing tie. So you can either get from the left to the right via this position, or the other way around, or perhaps because there's some noise, you can also break the tie again, so the game can become even longer. So that's a mini step. And let me quote from the manual of Arshena. So they say that this stochastic actor-oriented model can be regarded as an agent-based, actor-based simulation model of the network evolution, where all network changes are decomposed into very small steps. These are the so-called mini steps. One actor creates or terminates one outgoing tie. Quite importantly, I guess, for today, or at least the point I want to make, is that in the manual, Tom Snijders and others state that it does not necessarily reflect a commitment to or belief in any particular theory of action, elaborate in the scientific disciplines. So if it's not theory, then at least it's more or less an assumption that people behave like that. And it is assumed that actors change their score. Yeah? And they own that. And then it goes on, and then they do reflect about the mini step. However, I think that a lot of users of Arshena, whether it's for estimation or for simulation, go a little bit quick about this mini step assumption and what the consequences could be. Because it means that if we have a mini-step, there's no reactivity. The act of reaffirming, making, or breaking an outgoing tie does not trigger a response by the involved alter. There's no simultaneity, no joint actions, so changes occur one by one. Hence, also no cooperation, coordination, subordination, or negotiation going on in the model. At least not modeled into it. No altruistic behavior. Individual utilities maximized, no total utility, no strategic interaction. It's a very finite time horizon, no investments, and no forward-looking rationality. Yeah. However, I discussed this, of course, with Tom Snijders, and then he was. I caught him probably on a very rare moment because he had time, and then 2 days later he emailed me, yeah, I programmed reactivity in Arsiena. And so now there's some kind of reactivity going on in Arsiena. If you want, of course, it's not in the manual, so it's hidden. But as there's a lot of things actually are hidden within the software package. But yes, so now the act of making or breaking an outgoing tie can trigger a response by the involved alter in the original software. Okay, now this is what we are developing, and so this is the Arsiena 2-step. And what is the goal? So what I want to do is to provide a method to assess the extent to which the results obtained by the traditional Arsiena depend on the validity of the mini-step assumption. Or phrased otherwise, what if we have, like, if we assume or think about different theories of interaction? Then I want to test hypotheses concerning selection and influence processes under different theoretical assumptions regarding the theory of interaction. And perhaps along the way also then improve the chances to reach model conversion. So in Arsiena, quite a lot of those models do not converge as you try to estimate. And I think that might be because the true data generating process did not follow the mini-step assumption. So maybe if you use different theory of interaction, you can actually get models to converge. For today, the main point, or what the goal is to generate hypotheses regarding this theory of interaction. And in the ideal world, I would like to be able to test hypotheses regarding theory of interaction. Okay. So the sum of Arsiena as an ABM, so to generate a hypothesis regarding theory of interaction. When and why do different theories of interaction, so not assuming the mini-step, but making different assumptions, which I'm going to talk about a little bit later, make some emergent network properties, such as segregation or polarization, more likely to occur. And then to identify critical assumptions with respect to the theory of interaction. And please be aware that the mechanism of interaction, so now I'm not calling it theory of interaction, but the mechanism of interaction or the data generation process is unobserved quite often. You do not know what happens. Okay, so Arsiena 2-step closely follows the logic of Arsiena and the different theories of interaction, co-evolution of networks and behavior. Of course, I just started, so it's only uniplex directed networks, only 2 steps. So a lot of people say, okay, if you let go of the mini-step assumption, why not 3 steps or many steps? So it's only 2 steps, and estimation of the networks is slow. Everything is programmed in R. I did play around with plus, but it makes a little bit slow. Okay, the theory of interaction. We already discussed the mini-step. One actor, one step. The reactive step of Tom Snijders, one actor, one step, and that triggers a response by the alter. Yeah. With Arsiena 2-step, we also programmed the mini-step just as a check if I did everything correctly, more or less, but also a 2-step, hence the name of the package. 2 actors can make 1 step at the same time. Yeah. And also have a sim step that 1 actor can make 2 steps. Well, I think, okay, cool, that's it. Well, if you relax some crucial assumption, then you open the box of Pandora, because then it gets complex immediately, because 2 actors, 1 step, then you have all kind of options. Oh, I have different slides for this. Okay, so this is 2-step, jumping from this network to that network. And this would be the mini-step ways. Yeah? And a sim step would be this. Yeah? So now actor I can jump immediately to that network configuration. Yeah. although this would be necessary for the mini step, these pathways. Okay, but as I said, so the two steps simultaneously, two random agents can make a mini step at the same time. So that's one of the flavors, two-step. But you can also have two-step strict coordinations, strict coordination that agents connected at T1 may make a mini step at the same time. And then you have to define what does connection mean at T1, right? So that's also different parameters you have to tweak. And then we have recoordination, that only specific two steps are considered to be the result of coordination. So all steps of agents who were connected at T1 and all steps of random agents who became connected at T2. Yeah, you can imagine that perhaps that's because there's some other network which we did not observe that led to these actors doing something together. So the two-step is closely related to the one-step network foresight, probably, I think. I hope you agree. And adopting something together, crossing the threshold together, would be possible in this kind of sound, I would say, and that would connect to the talk of Francisco earlier today. Okay, so strict coordination, this is the network, and then these two actors can initiate the two-step. That's not that complicated, I would say. But this is a bit more complicated, the recoordination. Once again, these two agents can make a two-step, but these two agents can also make a two-step, but only these two steps that are possible for them. So this is their choice set. So these configurations are not counted as a two-step. And that's their choice set. Importantly, I think that Ashena two-step is able to mix the mini steps, a specific type of two-step and sim-step in one simulation. So you can actually see how important those different configurations are. Okay, I think with 20 minutes, if people not familiar with evaluation function, I can't explain it. The people that are familiar with evaluation function, I can just skip it. So the idea is that, okay, you have to evaluate the network that arises. This is the traditional one. So we have one agent, we have a network, we calculate all kinds of statistics on that local network of that ego, and then you optimize it according to the statistics that you put in. Okay, it's a bit more complicated if you have two agents, because how do we combine the evaluation of those two actors? So what I do, so we generate all possible networks of the two-step. Each actor is evaluating all these different options according to his own evaluation function. And I just sum those two evaluation functions, and then I do the normal method choice function. Yeah. So now the diet is the decision agent. And perhaps I am wrecking Coleman's boat. Oh, I actually misspelled Coleman. Okay, so now I'm still offending him. Even I don't have any question in it. Okay, but yeah, so the idea is that the diet is now the decision agent. I don't think this goes against methodological individualism because we are not observing the microprocesses anyway. So I think that if the modeling would be at the diet. Also, be aware that this is an assumption, right? How they evaluate their joint, how they jointly evaluate, because you can also think of other theoretical mechanisms. So coercion or maximizing differences in evaluation. So you see, if you relax one assumption, you really open. And when it's modeling the sim step, it's no complication whatsoever. When I presented this like last year on internet, everyone, then I did not have, it was not that far yet, and everyone was saying, you really need to be able to estimate, you really need to be able to estimate. So now I was invited for this conference, and this was about simulation. So damn, so it's always the wrong crowd, so to say, or me, the wrong timing. But since now we are able to estimate, I just want to show you a very quick example. This is more like ARCO, but this is the same drinking network of Glasgow girls. This is more or less a standard model that's included in all kinds of tutorials and manuals without degree, reciprocity, transitivity, 3 cycles, smoke similarity. Crucial here is that smoking and alcohol is here considered as time stable in this network. So here we're only estimating the network. Okay, so now we can do that according to all these different theories of interaction. And then you get all these numbers, and it doesn't really say that much. I think here the take-home message is that the estimates are actually very close together, or for more or less different specifications of the micro level. There are some differences. However, but so maybe then if I want to get this published somewhere, I need to find a test case where differences are more spelled out or come out, and see people see, yes, it can actually matter. But what we do see is that, so these are the estimates of the statistics, but if we look at goodness of fit statistics, for example, we do see differences between the data generation process. And in this case, the strict coordination is better able to predict the number of mutual ties and similar for some of the tried configurations. Yeah, so they do lead more or less to similar estimates, but there's different goodness of fit. Okay, now I'm jumping to a simulation example. So once again, oh yeah, you see I switched to dark mode in the meantime. Same network, but now behavior is a behavioral dependent variable, right? So it's dynamic. More or less the same network statistics. So similarity in smoking is in there, cycle, the 3 cycle effect, transitivity effect, an influence effect, average alter. Yeah, so a general selection influence model. Then, because it's simulation, we have to put in start values, right? So these are our parameters which we could vary. This is a vary. These are the values of the parameters I choose. And how did I get here? Well, first I just simply ran a normal Arshena model. Yeah, so I estimated the model, so I have empirical calibration of the parameters, so to say, and then I tweaked them a little bit for this for today. Yeah, and if I had more time, I would have all kind of distributions of the parameters. Okay, so then I performed simulations. Oh yeah, these are the more or less just 2 of the networks that came out of the simulation. I only did the 2-step strict coordination and the mini step, but these are archetypal examples. So higher segregation in the 2-step model, and also more polarization. So this is the alcohol value, of course, which ranges from, what is it, -2 to 2. So you see more segregation and more polarization in these 2 examples. But now the question is, do we see that in all kind of across the 100 runs of the simulations? The answer is yes, a little bit. So if you look at the mini step, so this is it's the variance or the standard deviation of the alcohol behavioral variable, which is an indicator of say polarization. And then under strict coordination, we see that polarization is a little bit higher. Even though the mean value of alcohol is more or less the same in the model. So we do see that one model is generating more polarization. And this is segregation. And although differences are not very large, we also see that the level of segregation is a little bit higher in the strict coordination. Yeah. If I had more time, I would have explored more of the opinion space. Okay, so what does it all mean? I think if we, from the estimation example, that there are some indication that both estimates of the network and behavior statistics and the goodness of fit may depend on the theory of interaction. But naturally, I only investigate one and probably not the most interesting data set and only a limited set of network and behavior statistics. But that's what we are doing right now in the process. So we're trying to find a nicer or better data set, and then a more structured analysis of, okay, where do we see differences and where would it actually lead to different results or conclusions with respect to network statistics. So what about the simulation part? Well, I think we already demonstrated the theory of interaction may impact the severity of polarization and segregation, or perhaps a bit more nuanced, or at least the speed at which it develops, right? Because it's not that this is a equilibrium that I show you, it's just the fixed rate function. I see that it develops. And naturally, once again, I only investigated a very small and probably not the most interesting slice of the possible parameter space, because I would be very interesting to see if with different parameter values under the mini-step assumptions, we would not get polarization, for example, and with a two-step, we would get polarization. Yeah, so that would be most interesting. However, we see that the sum of Arshena is being used as an ABM more often, but I think, yeah, more perhaps a little bit, as Christian, be aware that you're making assumptions, that there's things hidden in this model, implicit but probably important assumptions with respect to the theory of interaction, yeah, and that they may actually matter, and that it should actually be explored how important those assumptions are. And I think I had enough coffee because I'm finished.
Okay, this time, good audience.
Yeah.
Good fit, good fit. Okay, thank you. Please, Chris.
Question of understanding. So when you choose the two coordinating actors, those have to be connected by a tie. So you can only coordinate if you are connected in the network, or can it be any pair of?
It depends on the flavor of the two-step. The simulation is run under strict coordination. So then, yes, then you have to be connected. And but it's connected at path 2 and both by in degree and out degree. So that's what I've showed you. Okay, but you can read that, or you can. So there are different flavors. So the estimation is being done on all flavors.
Okay, so basically, then you can say you sample a tie from the network, and then you decide how the.
I sample not a tie. I sample a diet, right?
Exactly. You sample a connected diet.
Yes.
Yes. So I was thinking you sample from the network a tie because you sample two nodes on the condition that they are connected. So you're in a sense sampling a tie, connecting two nodes, and then those take a simultaneous decision. And I wonder just what this two-step sampling, where you first sample a tie and then like the one step further ties, what this could mean for the structure. And I was thinking about this disconnected network, that kind of you have clusters that are disconnected, and the fact that you have to sample a tie and then the simultaneous decision whether this could somehow induce already or make it more likely that this tie will then be more likely after the coordinated decision to end up in a cluster.
Partly, I would say. Yeah. No, but I may not completely understand you, because they should be connected at a two path, right? So it's not the tie between them. They can be a distance two apart, right?
I see. Okay.
Yeah. So that's one thing.
Yeah,
and
okay.
Their options of the two-step can be that they connect to someone outside their connection. So they're not updating their structure. So they have all options open again, so they can cross their own. They can connect to someone else, to a third actor. So with simpler models, we also see that. Yeah,
I see. Okay. Thanks a lot.
Any other question, clarification, please?
Yes, thanks a lot. That's super interesting. And actually, I remember when I was still with ICS, we had discussion with my economist colleagues with whom we studied mathematical models of network formation, that in Siena, we don't have all these far-sightedness that economists study. So in the sense, and coordination and so on. So I think it's really interesting. But I was wondering about one thing. So how should I phrase this? So I'm trying to imagine this modification that you're going after in terms of the transition matrix between between networks as states of this whole process. So in that sense, if you have a two-step, you make this kind of a longer jump as opposed to this mini-step situation, right? So to what extent this modification changes? So is it possible to make a jump between two states to which would not be made with the mini-step by the two-step, right? So in a sense, is it a shortcut in this state space? Or does the model then allow to make a jump that will be impossible otherwise, right? So I was thinking about it not only in order to understand the consequences of this extension, but also can it give you an inspiration of what kind of empirical setting might be interesting to look at to find the data set that will exaggerate, I mean, that will allow you to show the importance of it. So if you had this one slide in which you had two connected actors that were making two ties to a different people, right? So for example, such a two-step will not be a shortcut in the sense that there's just made, for example, if these ties are strategic substitutes, right? So in a sense, if the mini step through which we would create the first one will make the other one not attractive anymore, right? So I was wondering whether you thought about.
Yes, we're thinking about that. Yeah, we're thinking about that. And for example, threshold models that you need to coordinate before something becomes positively evaluated, that you need to coordinate. So yeah. And what we actually see also in the goodness of fit is that reciprocity is higher in the two-step, right? So because I don't want an additional tie with you, only if you reciprocate your tie. So this is very simple. Yes, it's very simple. And the same also for sensitivity, right? It's easier to get there. And then Tom's argument is, yeah, well, but with the mini step, I will get there in the end. And just just need me.
It's a shortcut.
Yeah, it's a shortcut, but then yeah.
Okay. Thank you very much. Brilliant. The last presenter is Daniel, right? You? Yes.
Cool stuff. Yeah.
This one? Yes, thank you. It's not mine. Yeah.
So, yes, so thank you so much for inviting me to speak. I really appreciate the invite. Thank you for the organizers. My name is Daniel. I'm a PhD student of Andreas, as well as Vincent Svej and Tobias Stark, as well as experience in social psychology at Groningen. I'm also funded by Scoop, a sustainable cooperation. And yeah, this is not an ABM, other than the fact that it's a Siena model. So I guess we can say that's an ABM, and I have 2 or so slides and simulations about my missing data. But other than that, it's a normal paper presentation. Hopefully it's a bit more digestible today. So it's entitled "Who Would I Like to Know?" So surface and deep level traits in the dynamic friendship process. And this sort of begins with asking the question of, first off, how do people become friends? This generally being demographic homophily. This is quite well known that you are attracted to people who are similar to you. There's Asfeld and Merton in there, sort of seminal. It's a status model. Demographics predominantly. In this case, we look at race or ethnicity, gender, but it's generally seen as a timely way to establish friendships with individuals that are similar, right? So you see the person's sex or gender, you see the color of their skin. Generally, it's the first sort of thing you pick up. However, this isn't necessarily how you keep friendships, right? You're not necessarily friendships with someone just they're the same gender as you because they're the same ethnic group as you, etc. Rather, you share passions, you share hobbies with the other people that you can do together, right? This is what Lazarfeld and Merton call value homophily. And empirically, this has been seen, similarities between friends in playing video games, engaging in delinquent behavior, playing football, etc. They see similarities that sort of keep you together. However, following this process of where you first establish your friends based on demographic characteristics, and then you sort of maintain them on non-demographic characteristics, there's this sort of, I use the word segregation over here, but there's the split that remains, right? So your limited access to friends that are similar enough to you in these, what we'll call deep level traits, creates this lack of access between one another. So let's say these two squares over here and the circle over here really like being read. They would become friends with one another if they were exposed to each other in an early stage. However, because the shapes were the initial, surface level or easily to interpret characteristic in which they separate each other and become friends with initially, they don't actually get to access each other and know that they like similar things. So this then leads to the research question of, on what commonalities do people create friendships with one another? Is it demographics? Is it correlated values? Is it their own values? And also, how do these change over time? How do these friendships maintain over time? So we want to examine on which easily or more hidden traits friendships are based, how time plays a role in the development of these friendships, and whether hidden traits almost become more strong or a more substantial base of friendships than these surface level demographic ones. With an overarching goal that I'll touch on in the end is to see, well, okay, if there is a sort of separation on demographic traits initially, is making salient certain deep level traits of interest, passion, and hobbies a way to sort of reduce segregation among people who might have established that in the first place. Now, quickly to settle some terminology, what I'll focus on is what, I've called status homophily, but I would call surface level traits in this context. It comes from organizational literature from Catherine Phillips, basically saying that obviously these are the easily interpretable demographic traits, but more value homophily or deep level traits, which I call them, are traits in which in organizational literature sort of show more success in creating teams, creating a positive environment in an organization. And also in the context of my project, I'll eventually begin looking at cooperation. So whether forming groups not necessarily based on demographic traits, but rather on these deep level traits actually leads to more beneficial cooperation in the grand scheme of things. Now, for an illustrative example, I'll use my nationality because I can stereotype myself. You get, South African that you would deem become friends with each other because of South African, because they're all South African. However, research has shown of these sort of byproducts or these demographic byproducts, right? So you're not actually friends with someone because they share the same nationality as you, but rather you're friends with them because they share the same common characteristics that might be carried by this national, context that happens. So for South African, maybe you like, rugby, warm weather, going on safari and stuff. So you might become friends based on, both liking rugby or whatever. However, if you were to completely block these demographics or these nationalities in this context, they would still become friends because they like the similar things. But the third person over there, who was also South African, would not become friends with them because they like cold weather, they're vegetarian instead of eating meat, and they prefer playing video games instead of, going to play rugby. So based on this sort of process, you get social identity theory, which is based on the identity of, nationality, gender, whatever, but it's carried by these ethnic byproducts of sharing the same similarities in terms of what you do, what you like doing, sort of what you're passionate about. So given this, in completely no context of, nationalities, demographics, etc., the similarity attraction paradigm would then, sort of say, well, if we have three random people over here, how would they become friends with each other? Who would become friends with one another? And this is generally done in isolated cross-sectional studies of, seeing if people share the same similarities in terms of playing video games, playing sports, engaging in different behavior. But we want to extend this basically by looking at the dynamics. So as I sort of painted out this picture of getting to know someone initially, as this time progresses, do you stay friends with them once you realize what they're interested in? Because obviously, I don't know who's interested in football, I don't know who's interested in video games, etc., until you actually spend time with them, get to know them, right? So you might get the case that people become friends based on nationality, but then you realize, well, actually, we actually don't share much in common other than that. So they fall away and become friends with other people that share sort of similarities in this. So then from this, we develop a sort of series of hypotheses following this sort of process that what we call surface level, as I said, demographic characteristics shared between individuals would lead them to become friends. This is the plain, simple, homophily based on demographic characteristics that they would like to be friends with one another who share similarities. However, we propose that over time, these shared similarities actually become a weaker predictor of friendships. So once you realize that you don't share much other than nationality, you might not necessarily have the strength of friendship. They might fall away eventually over time. You're no longer friends with them. We propose a similar dynamic based on these deep level characteristics. However, the second one is switched. So we say that while these characteristics, deep level characteristics shared between individuals drive friendship formation in general, we actually think they become stronger over time. So once you get to know exactly who's who likes similar things to you, who enjoys doing the same things as you, these become the solid base of friendship. And that's not to say that homophily completely falls away. Demographic homophily is still going to be there, but not necessarily an overarching sort of a theme that is generally proposed. How do we look at this? We use the Swiss student life data. We are using the first year of students in the Swiss student life data of cohort 3. Removing, it says isolates there, but basically removing people who haven't participated in the first 5 waves. We have 586 respondents, predominantly male and predominantly Swiss. However, there are sort of a nice range enough to see these dynamics in play. We action demographic covariates as being either an international student or a local student, as well as sex, either male or female. There were only male and female respondents in the survey. What we call trait covariates here, or what I'm saying are these deep level characteristics, we use in-degree nominations for certain questions of perception of other students in the cohort. So who do you think is smart? Who do you think goes out to party a lot? Who do you think is social? Using in-degree nominations from this, we sort of get a ranking. I say ranking, but we sort of get, okay, this individual is nominated 12 times as opposed to this individual is nominated 3 times for being smart, let's say. So we can generally assume that the person who's nominated 12 times might be smarter than the person that's nominated 3 times. We also control for knowing people before you enter the first university year, and this is also important that it's the first university and it's as they enter, because we're sort of looking at this process on a scale in which everyone is meeting each other at the same time, getting to know each other at the same time, and then eventually maybe changing their friendships at different times to sort of see if it fits both deep level characteristics which we propose. And we use sales, so mainly focusing on similarity effects of these nominations, same effects on sex and nationality, or nationality, I'd say Swiss, non-Swiss, or international student or not. And what we do is we interact time dummies individually in separate models without covariates of interest, as you'll see in a sec, to basically see, okay, well, over time, over these different waves, because it's 5 waves over the first year, which is really nice, but it's 2 months sort of separating it. So you get this quite granular data to see if it changes in this first year. So we interact these time dummies to see what is the effect of this over the different waves. So to start with a couple of descriptors and some networks, just to make sure that this is actually conducive to some sales. We see a general applicable Jacquard index for CNN analysis, as well as the expected degree, some changes, between the sex or whether it's an international student or not. And also interestingly, some decreasing segregation matrices based on sex and nationality in the networks over the waves. So either there's a random process going on, people just, relying less on demographic characteristics to become friend, or something is replacing this. And that's what we sort of want to see. So the one sort of caveat with the data is that some of the waves, the response rate sort of decreases over time, and also it's important to note that it's actually not always the same individuals that are absent, but they might have been absent for a certain day of the respondent of the survey. So as a result, they're not there for one wave, and then they appear in the next. So what we've done is multiple imputation from Robert Krause and his supervisors while he was at Groningen, which basically we use the incomplete networks as well as our covariates of interest, so this being the surface level and deep level characteristics, to create a simulated network in these different waves, and then using the previous wave as well as the current wave's incomplete network to create the complete network. So for this, we develop basically 5 networks per imputation, where the completed networks are basically draws from a distribution based on these covariates of interest in the incomplete waves, and we do this 30 times. So we have 30 completed networks, and then we run 30 Siena models. It is almost sometimes advised that you do more, but at this point it's taking a couple of weeks to do an individual model. So we're sort of cutting it off by 30 and saying, okay, well, also we're not seeing much change after the 20th, 25th. So 30 seems to be a good enough number. And the result is that we get a big table that I'm going to shorten in the presenting of the results to you. So it's also important to note that we do have all the structural effects that I mentioned as well as including ego effects, alter effects, and controlling for a bunch of things. But I'm just showing you the similarity effects because that's what we're interested in. Also show you everything, especially with the time dummies. It sort of exponentially increases the length of the tables. So in the baseline models, what I say is baseline is not including any time dummies for anything, but just seeing, okay, well, is there actually homophily on surface level characteristics and deep level characteristics? Thankfully, there is. So we haven't been completely non-fruitful in our initial studies. That, as expected, this homophily on both sex and whether or not a student is international or local, as well as homophily on whether a student is clever, whether a student is serious about their studies, and whether the student parties. So this is a good indication that, well, friendships are based on demographics, are based on these, certain surface level characteristics, but also on deep characteristics. So what we then start doing is interacting our covariates of interest listed on the top there with our time dummies, and we see some more promising things that actually we see in time dummy 2, 3, and 4. So these are the subsequent waves in comparison to sort of the first wave, that there's decreasing reliance on these demographic characteristics. So compared to the first wave, second wave, third wave, and fourth wave, it's less likely that being an international student or being of the same sex is a predictor for friendship. So, you sort of think, what takes this place? And unfortunately, we don't find that for our nomination-based deep level characteristics. So there's no real pattern of significance in terms of the time dummies. What is important to note as well, though, is that it's very consistent in terms of the baseline model. So we included, obviously, the baseline models in our analysis across the board, and it's very consistent. So at least saying that, well, there's something there, but not necessarily what we have captured in the time dummies. So there is baseline homophily based on both our surface level and deep level characteristics, but they don't necessarily change over the first year based on these nominations. So sort of looking at these lack of significance in the deep level characteristics, it begs the question for three sort of explanations. The first one is that there's a problem with in-degree nominations. You can imagine this can be the case. In-degree nominations may be biased. You may be friends with a bunch of people. You only nominate who goes out the most within your friend group, who is the smartest in your friend group. So you don't actually get this whole picture of the entire cohort. You can't easily know 580 people. So you just nominate within your friend group. Alternatively, this process happens significantly earlier. So not necessarily within the first 2 months, within the first year, but even within the first 2 months. Or alternatively, we just don't have the correct variables to capture this process. Obviously, we're focusing on sort of two general concepts that are separate enough, but sort of similar, maybe, and it's highly probable that, these aren't the only two aspects that are relevant for friendship among students in their first year. So what we do to at least negate this first point of bias in the nominations is that we look at the big five personality traits. So less robust than maybe interests and hobbies in terms of creating friendships. But there have been some models that basically are showing that there is friendships based on the big five personality traits. So that's being openness, conscientiousness, extroversion, agreeableness, and neuroticism. In the Swiss Student Life Survey, it's action through 9 questions per construct. It's a self-report, which is important that there's no real way to bias this. Well, you can if you try, but I think not very easily. So at least if we're finding a similar trend with the self-reports, we might be able to negate the fact that there's bias in the friendship nominations when it comes to these deep level traits. So going along the same sort of process that we did, we are, again, luckily seeing significance in our surface level characteristics, and less, but still there in some of the big five personality traits, being conscientiousness and extroversion. It's interesting because, it comes and goes. And also, if I was to get into the dynamics of the ego and alter effects, it becomes a lot bigger of a story, because you're not necessarily just becoming friends or the most agreeable people, but rather people want to become friends with someone who's very agreeable, or people don't want to become friends with someone who's very neurotic. So in sort of the similarity aspect, it's not as strong, but there is still something over there, as we can see for conscientiousness and extroversion. There's still decreasing effects of the demographic traits over time. So it's positive that also we are not seeing anything in sort of the time dummies of the big five traits. So Obviously, there are here and there with negative effects in the third wave. It's also, you'll see when I sort of show a segregation indice that the third to fourth wave has a sort of interesting quirk to it. But nonetheless, we're not seeing something that would indicate that we are biased in our nominations for friendships. So in looking at our hypothesis, we can confirm a bunch of them that both surface level and deep level traits are significant enough for friendship, and that we can see that demographics sort of are decreasing over time, but we don't have this compensation of our deep level, surface level traits are decreasing over time. We don't have this compensation in our deep level traits sort of acting as positive, sort of replacing this lack of reliance on demographics. As I said, this could be for the two reasons of this process happening much quicker than just a year, but rather within the first 2 months, or it's processes that are taking place that we just don't necessarily have in the data. Now, as I mentioned, we also consider this in segregation. So you would think, okay, well, decreasing reliance on these demographic traits might lead to less segregation over time based on these demographics. And we look at it over the 12 waves over here, just to see if there's a decrease. And generally, so the two different colors are two different segregation indices, and dotted lines are for international students, solid lines for being of the same sex. In general, it decreases, but there are interesting quirks of the data. So as I said, from wave 3 to wave 4 and wave 5, there's actually an increase again. So there's almost increasing segregation based on demographics. It's important to note that this is the time after the December break, which is a bit of a longer time, and also December break is a time that you're not necessarily seeing the people at university. And then within the fifth wave, well, just after the fifth wave, they write their first year exam, which is very important in the Swiss system because it's basically if you pass it, you carry on. If you fail, you have to repeat the year. So we also see less density, less friendships being made in general in the fifth wave. So those are an interesting sort of caveat, but at least overall, we see that there is decreasing segregation based on this. So if we were to run the model for the entire year, which we didn't, because from sort of after the first year into the second year, you get people almost coming into the data set who weren't there previously because they might have failed the exam in a previous wave and then sort of passed this one. So now all of a sudden they increase, so they're on sort of different times of their friendship timeline, if I can say, and it sort of ends up in biasing the data a bit to different timelines. But nonetheless, the key takeaways that we found is that at least demographic homophily faces the dynamic process, which isn't always, oftentimes there's either homophily on demographics, there's not homophily on demographics, but rather we see that it sort of changes over time based on how familiar people are with their cohort, and that they are friends being based on demographics and non-demographics. However, the actual non-demographics that are at play here is more, weak than we can sort of in the data that we have, but it would be cool to find those. And yeah, the results on segregation is very complex. It has a lot to do also with the context of the data. And there are obviously limitations to be considered and tested. More robust measures of nominations are, I think, the most pressing issue, but then also the opportunity just to test a more range of them to try and find what is compensating for these decrease in demographic reliance. Yeah, and with that, thank you.
Okay. Any question, comment, suggestion?
Well, super cool. Nice to see the data being used by someone else. So a few thoughts that I had. So I agree with what you said about that you're conditioning on the previous wave. So basically the first model that you're showing is already between wave 1 and 2, and wave 2 is after a month. And you could imagine that a lot is happening in this month in terms of getting to know people. And I think it's good that you accompany this with descriptives that are focused on the waves, because indeed first wave is the very first week, where probably many people indeed, and I think your descriptives show that had to rely on more like the obvious signals rather than deeply getting to know each other, even if they report people as friends. Based on how you kind of develop your hypotheses, I was actually thinking that you're looking into what makes a tie more likely to survive versus one being newly created. And of course, you're probably aware that there's all this toolbox to do this. Because this is a pretty large community, these are a few hundred students, and you can meet completely new people or still after 3 months or 4 months. And this is still a new tie, and you might still rely on kind of the surface level signals and then get to know people. And this would then be reflected in whether you maintain this friendship. Yeah. I was wondering what your thoughts are on why you decided to go down this road, just looking into time dummies rather than operational maintenance processes.
We sort of thought that it's a large community, obviously, but in terms of what we action as our deep level variables, being a smart student or being serious about studies, being someone who's very social and party, going out to party a lot. These are obviously, you might meet someone based on the demographics, as I said, and then get to know them. But these are also things that, right, you can see maybe from a distance. So if someone's staying at the library or at class very early, asking a lot of questions in the seminars, you might implicitly already assume that they're dedicated to their studies and smart. Same with going out to party, you might see them in social contexts more often. So although you might first initially meet them based on demographics, you might, as time progresses, there's a familiarization hypothesis. I can't remember the author, but basically in a cohort, as the cohort continues up through, seeing people around, not necessarily interacting, through rumors, through getting to know, about someone through someone else, you get this implicit, picture of them in your head as time passes. Obviously, it's not as robust as someone to say, going up to you and say, hey, I'm whoever, and I'm a smart person. But you sort of do get this implicit idea of someone as time passes. So as you said, it's not exactly, the most science of, you get to know everyone at the same amount as time passes. But using the time dummies then at least sort of allows you to then, someone to pop up and you socialize with them already from a point of, I know you because I see you at the library a lot, so that must mean you're dedicated to.
Can I very quickly, just a quick follow-up? I get the point. Maybe, however, this is something you might want to explore descriptively in the same way you've done the other descriptors, like looking into whether the characteristics of dissolved ties versus maintained ties, whether they are similar and whether there's maybe a trend through time.
That's actually a fair point. You don't need to look much at the dissolved tie.
Thank you.
I'm just thinking more about indicators of just seeing each other a lot. Do you have basic things like what subjects they're studying and so on, so they've got common classes?
So in if I'm correct, and Chris can correct me, but in the first year of their studies, it's all sort of simultaneous. So they're all following the same courses and the same lectures. I'm not exactly sure about the tutorial groups and the project groups, etc. But at least they're following the same courses. They're doing the same type of work, etc. So there is reason to assume that they would bump into each other. It's also a technical context. So it might be a lot of tutorial groups, a lot of opportunities to sort of mingle with people who might be in the subject that you might not necessarily come into contact with.
So actually, I saw you cited Linda Zhao's 2023 paper study about the probability surplus consolidation effect. So it reminds me of some effect of consolidation, especially because her finding was if the classrooms, the students consist of students whose ethnicity and social status are correlated, then probably the racial homophily is more likely to happen, something like that. So from that point, actually, I can imagine something like you said, it's a demographic homophily and non-demographic homophily. You said it's a very independent variable. Consider that, but probably in some schools or classrooms, this kind of correlation may happen, and then it may affect their friendship kind of things also. So did you also test this kind of possibility?
That's definitely a fair point. It's with the sort of coinciding cross-cutting social circles and reinforcing, I think also, the reinforcement of one another. we can look at it, but then we also, with the time dummies, we get into three-way interactions in ASEAN, which it's a lot to go through. And then it's, there's the data has, as we said, a lot of males, a lot of Swiss. So that's a fair point, especially within these groups. I think there will be a lot of that, but it's also outside of these groups, right? So it's also you can imagine the female non-Swiss population of the data is probably quite small, in that it's quite unlikely that they would have also sharing the same hobbies, passions, etc. So this sort of cross, at least be able to capture the sort of cross demographic lines in this. I think it would be really cool to look at that, but I'm frankly scared of three-way interactions and not yet.
Well, you use ASEAN to estimate or to test your hypothesis, but I have the feeling that would be better off going to egocentric network data based on on the information you have, because then you start with guys that are there and then estimate if they are broken, and you actually know if they are replaced with someone similar or with someone different.
Yeah.
So I think we can discuss it later, but I think maybe you get closer to your hypothesis if you use egocentric data, and it's much easier to model all these time effects.
Yeah.
So it would be interesting. I hope Miranda agrees. I said he's egocentric expert, but yeah.
I think that's exactly also if I had an idea about similar to this, but then sort of seeing these demographic makeups, and then sort of someone running an agent-based model on these demographic makeups of these different time points to see if you can see what might cause this based on a bunch of different parameters of the egocentric network. That makes sense.
Okay, any other question? So thank you very much, Daniel. Yeah. So I'm seeing that we have recorded 9 hours presentations and discussions. So I guess you probably have done a lot today. However, given that we also have some tests tomorrow, there are presenters also tomorrow, but maybe we have also time to talk about later setting. So I would like to just share with you what I feel it's relevant to discuss tomorrow. Yeah, after. So my impression is that I mean, there are different type of approaches in this small group, but very much synergetic in a different direction. So which is something that is very positive. And a thing that I was thinking is about that there is someone else missing in this group of people. And that could be probably one of the lines for future type of events to try to outreach other experts in other field, in other domains, which has been also cited. For instance, I mentioned also Karui, for instance, all these kind of people from game theory, which study net information with a game theoretical framework, could be probably friends of ours in the next step. I'm also, this is something that we discussed within the Behave Lab. There is also a bunch of people more from the cognitive science studying the cognitive aspects of network mapping, net information that could be probably also relevant to reach in the future events, which could be probably important. So I will probably consider for tomorrow to discuss which are other group of people can be probably interested to talk with us in this line. Another thing will be that I'm not a super fan of polarization debates, in my opinion, but I grew up in the conflict theory about society, so it seems to me more I don't know, normative, progressive point of view. So I'm not the guy obsessed by polarization in society. It's to me very much a normative position more scientific ones. So a thing will be that if someone else will jump into this room from not our own type of modeling attitude, my impression that this guy will not have considered very much diverse point of view. So, and the debate was obviously dominated by methodological modeling type of thing. And another challenge from my point of view in terms of perspective and understanding which are the relevant social puzzles on which we believe that investigating better the net information mechanism, the interplay between behavioral aspects and network could make the most relevant difference in perspective and to identify these kind of topics and understand probably it's valuable. There's a positive marginal utility in maybe pointing the effort of this group towards that direction instead of that one, because we might expect that in that kind of domain we can make a huge difference. This kind of effort. That's another point that I would like to make tomorrow. Then I'm super happy about today. But please, now it's time for you to reflect about Andreas.
I haven't heard you say, I agree with a lot of, not everything, with a lot of things you said. But I have
not about polarization, I assume.
Well, we have a bit polarization maybe on that. I haven't heard you say anything about experiments.
Yeah.
But I believe experiments are one of the other tools we have in our toolbox to help us better understand certain particular mechanisms, maybe also test some of the more macro level implications under controlled conditions. So my suggestion would be to add it to the list of things to think about.
Yeah, that's the So maybe getting this kind of behavioral game theories, which are those one who actually linked with the game theory framework, that they appreciate the idea to test this kind of hypothesis in a lab or in experimental measures. Yeah, very good point. Any other would like to? What else this could be relevant to discuss tomorrow, Indy, so that we can start thinking about with a glass of wine later. So do you see any value in maybe setting up or discussing tomorrow's possibility of a joint effort for a special issue in a journal to state of the art, and this is also to elicit contribution by people who are not part of our networks that might be probably interesting. Do you see that as a things to work on? See a lot of this stuff. So let's talk about this in a glass of wine. Yeah.
Needs to have some concrete topics. What I can think of is indeed again more of methodological direction, and I don't know if we want that. Yeah, I mean Joachim's initial slide, segregation, polarization. This kind of covers a lot of what we all are doing, and.
Yeah, so I mean, your Christian, your point was it's better to start with a topic or a bunch of topics in which this kind of research can show the added value and build on it, also this kind of methodological implication stuff.
I think yes, because otherwise you get again more modelers, which
is not.
I think we didn't necessarily want. I know people, or I know about people from the US who do actor-based models of networks from an economics point of view, for example. They have their own approach to agent-based modeling of networks. So they could contribute to this as well, but would be a completely different orientation, I would say. So I think we need to think twice about what we will do.
Super good point. Yeah, very good. Any other? Any comment or point from the online audience? And be probably hard to follow 9 hours of people speaking in Milano. Probably, yeah, but still alive. Right? Still alive people around. So if there's nothing against my decision, let's stop this long day. I would like to thank all the presenters, all the audience here. I hope that you enjoy that. So we'll be back here tomorrow at 9 o'clock. We have a long list of a presentation, right?
Social dinner tonight. Dinner tonight.
There is a social dinner tonight for those one who are in the external invited speakers. So it's
8:30
the Bianca
at the same hotel where you staying.
day. So yeah, let's.
And I'd say before that, since you were speaking of a glass of wine, I mean, for those of you who want to grab a drink or two together, I don't know. Either you stick around and then we can leave.